screen. Randomize it all that we're not 30 people. Sometimes it's kind of nice to be a slightly small group. Okay. So you should be able to see your presentation now. Can you see it full screen? Brilliant. Okay. So yeah, today's talk will be about. In fact, yeah, it's very nice. Maybe I should say first that to give this presentation here, because this is very much a Cambridge project. So I mentioned earlier, I was a postdoc in zoology for 5 years, and so was Fangan and Phil. They were both postdocs in zoology as well. Andrea Manica is a professor in evolutionary ecology based in zoology too, and Tim Rademacher is a former PhD student in geography. And yeah, this is a paper that we worked on for many years, and that was recently published in a nice journal, which we're very happy about. It's going to be about how could relocating global croplands help to decrease the environmental impact of agriculture. And so just to sort of kick us off, something that will not come as a shock to any of you, agriculture doesn't just provide food, but is also responsible for significant environmental impacts. And the 3 impacts that we're going to focus on in this talk are carbon emissions, namely in the form of the loss of carbon that's stored in the natural vegetation, and when that natural vegetation is lost in the process of the habitat being converted to cropland, that carbon eventually is lost. Burning the vegetation is the most direct way in which this can happen, but there are other ways too. And soil carbon with vegetation carbon is particularly visible how the carbon is lost, but soil organic carbon also decreases significantly in many cases when natural habitat is converted to cropland. The second type of impact that we'll be looking at is biodiversity loss. So agriculture is a major driver of habitat destruction, and habitat destruction in turn is the most important threat to terrestrial biodiversity. So agriculture has a major role in that respect as well. And finally, freshwater use. Agriculture is responsible for about 70% of freshwater use, which always seems just so high when you think of taking your shower in the morning or making food or putting on your laundry, and you think, oh, so much water use, but none of that is comparable to what we use for food production. So I think one of the motivations behind this study was that all of these impacts that I just mentioned are distributed very heterogeneously across croplands. So there are parts of the world where we produce food very efficiently with very little impact, and there are areas where we produce hardly any food at all, but impacts are tremendous. And there's we included in the paper a nice little quantification of that. I find that quite useful to sort of motivate the rationale behind the study. We combined 2 different types of data. The first one is crop data, which are from 2010. There's now an updated data set that appeared only a couple of months ago. I think there's always quite a significant delay in global crop data. First type of data in this data set are maps of the harvested areas of individual crops. I think what's shown here is maize. So harvested areas on the one hand and yields on the other hand. And we combined those with maps of environmental impacts, and impacts throughout the presentation will define as the difference between the natural state and the crop specific state. So for carbon, that means how much carbon is stored in the natural vegetation as opposed to how much carbon is stored in the crop, and both with regard to the above ground vegetation and to the soil below ground. And exactly the same applies to biodiversity. So we're comparing biodiversity for the natural vegetation and for the crop specific vegetation. If you ask 10 people how they measure biodiversity, you'll probably get 11 responses. The particular measure that we used here is called range variety. It's essentially some kind of species richness measure that puts higher emphasis on small-ranged, rarer, more vulnerable species. But we repeated the analysis with the standard species richness measure, and the results were broadly quite similar. So what we did with those two different types of data is, for each crop, we sort of traversed all harvested areas and looked at what is the impact in a given crop cell, in a given grid cell, relative to the crop production that we get in that cell. And the resulting graphs, which I'll explain now, are these ones. So here, each gray line represents a specific crop. And on the x-axis, you see the total production of each crop and globally, and on the y-axis, the total carbon impact, and on the bottom panel, it's biodiversity impact rescaled, so you can compare across crops. And what each line shows is essentially running through what I said before, running through all of the grid cells, and now ordered according to how much impact is generated in that, or what the environmental impact is in that grid cell relative to the yield, ordered in that way. So what that means is down here you have all the grid cells where crops are produced, where you get very little production. These areas are not particularly productive, but environmental impacts in these areas are very high. And up here you have the opposite, where you get a lot of production for very little environmental impact. And so takeaway message here from this carbon specific panel is that about 25% of the production of each crop causes half of the carbon impact of that crop. For biodiversity, it's even more extreme. Here we have about, I think, 8% of the production of the crop causes about 50% of its biodiversity impact. And so the question that arises from that is, what if we only produced food up here where we get a lot of production but for very little impact? That's kind of the rationale behind the study. And at the same time, what if we return these areas here where we have a lot of impact but very little food production? What if we return these areas to nature, allowed these areas to regenerate and grow food elsewhere? And of course, that only works if abandoned cropland actually regenerates and recovers its original carbon stock and biodiversity. But what we know from empirical studies is that that's generally the case. So of course, there's a high context specificity there, but especially for carbon, you can expect after a few decades, you can expect carbon stocks that are actually quite close to the pre-disturbed state. For biodiversity, it's even more context specific. There are fewer data there as well. But again, at least in terms of species richness, after several decades to maybe up to a century, you're back to the original species richness at least. And then for species composition, it can often take longer. But essentially, we see a similar recovery trajectory. So there's a lot of, once the cropland is abandoned and vegetation comes back, biodiversity follows quite quickly as well. We have this sort of asymptotic recovery. There's a lot of recovery at the beginning for both carbon and for biodiversity, and then it levels off towards the end. And it's just a sort of an order of magnitude of how many years it takes for biodiversity and certain ecosystem indicators to recover. And as you can see, the general order of magnitude that we're talking about is decades to maybe up to a century. So this is quite promising for a strategy that involves abandoning and relocating croplands. And so this is a bit of I mentioned at the very beginning that I gave this presentation a couple of weeks before to quite a technical audience, and so there's one slightly mathematical slide here, but I'm going to just whiz through most of the formula. And essentially, what this slide is meant to do is to give a little bit of an idea of what is the methodological framework for what we're trying to do. So our goal is to determine the optimal distribution of global croplands that has the smallest possible environmental impact. And for this, there are three conditions that our model, if you will, satisfies. The first one is that we keep we want the total production of each crop to be the same after this hypothetical relocation. So this is an assumption that could obviously be relaxed, and this is something that I'll speak to a little bit at the end of the talk. But for this exercise, we assumed that before and after the redistribution, the total production of each crop is the same. So our analysis does not assume any diet shifts or anything like that. Yeah. For that, in order to, in mathematical terms, what that means is if you have your total production of some crop I at the moment on the right-hand side of your equation, what we want in our optimized scenario is so what we're after is for each crop is the harvested area across all the grid cells. So we want to know where are the harvested areas of crops in the optimized scenario. And once we have those harvested areas, we need to know what's the production of that crop going to be in a given grid cell. And if we combine that across all grid cells, then we get production in the optimized scenario. So we want that to be the same for each crop as in the current scenario. And one data set that's relevant in this context is what is the production going to be of a given crop in a grid cell where it may not be cultivated at the moment. And there's a fantastic data set generated by the UN Food and Agriculture Organization. I'm just going to advertise it here a little bit because I think it's really fantastic. We made extensive use of it, where you can specify the time period that you're interested in. This is obviously historical data. We ran the same analysis for future data, which I'll have a slide on later on. And then you can choose for future data different emission scenarios. You can obviously choose the crop, the type of water supply. What we looked at is specifically rain-fed water supply. So all of our results are based on the assumption that there's no systematic irrigation whatsoever. So whatever our inferred optimal distribution of croplands is, by construction of the approach, it is not going to need any systematic irrigation, just by the nature of the data that went into it. And then there's a distinction between different input levels. So those reflect the sort of management level of the crop that ranges from traditional subsistence-based agriculture, very organic, very little fertilizer use, very little pest control, traditional cultivars. On the one hand, that will be a low input level, and the high input level is fully commercialized, fully optimized agriculture, mechanized, optimal cultivars, perfect fertilizer application, etc., etc. So for each of these different scenarios, you get a different map of what the expected yields of that crop under this particular scenario would be. So that's an important input for our analysis. The next condition, after the one saying that we want the total production to remain unchanged, is that obviously new cropland does not exceed the available area that can be used for cropland. The map we use for this is everything that isn't water bodies, crops that we didn't consider in our analysis, pasture lands, areas that are generally unsuitable for agriculture due to soil and terrain conditions, as well as protected areas and urban areas. So all of these areas are excluded from where cropland could potentially be put in the future. And within the remaining area, we can distribute cropland as we please. And finally, again, the mathematics are not so important here, but finally, the final ingredient for the optimization routine that we implemented is that we want to minimize the total carbon and biodiversity impact. So we've already sort of minimized the water impact by using rain-fed yields. And so our final step here is to minimize the carbon and biodiversity impact. And in the first step, we minimize these simultaneously. So there's a way to compute what the optimal trade-off is between those two, so you can minimize them at the same time. And later on, I'll say a little bit about what the trade-off is between minimizing carbon and minimizing biodiversity. Okay, these maps we've already seen. Okay, so here's a map of the current distribution of global croplands. We looked at about 25 major crops. They account for almost 80% of all croplands in the world. This is the current distribution. And if we run our optimization routine, this is what we get for the optimal distribution of croplands. In general, there's very little overlap with the current distribution. We see a few major clusters. There's one here in the Corn Belt, I believe. One important here just south of the Sahel zone, a little bit here in Argentina, something here, little bits and pieces. These are areas where where crop yields would be extremely high and environmental impacts in relation to those crop yields would be extremely low. And what would happen in terms of impacts if we grew food in those places? There's a comparison here of the carbon impacts of the carbon biodiversity and water impacts. You can see the Y scales here. And for carbon impacts, we would have a reduction of over 70%. Biodiversity impacts, the reduction of the impact would be almost 90%. And water, as I said, by definition, this configuration here does not require any irrigation water whatsoever. What that means in practical terms, 70% of carbon impact reduction, that's equivalent to 20 years of our current net CO2 emissions. Yeah, so it would just put a sort of a halt to climate change for a couple of decades. For biodiversity, the impact reduction is obviously even more extreme. Pressures on terrestrial biodiversity would be massively alleviated in this scenario. And for water, it's even more obvious. Water shortages in arid areas where agriculture uses a lot of water will be reduced quite significantly. Okay, I mentioned at the beginning the potential yield data that we used is also available for the future, and I have just a very short slide here. This is what the optimal configurations would look like under different future climate scenarios and for climate at the end of the century. So all of the current maps that I showed before are for current climate, and this is for future climate. And the takeaway message here is that the areas remain broadly in place. There are a few changes compared to the current climate, but in general, the optimal areas for future climate, no matter what the emission scenario is are broadly similar to the optimal areas for present climate. What that means is if we establish optimal areas, if we establish croplands in optimal areas today, then they will largely remain in place in the future. Our previous analysis, they assumed that we relocate all croplands across national borders, and that's obviously an extremely unrealistic scenario. So we then spent the second part of the paper relaxing this assumption and making it trying to make the analysis a bit more realistic. And the first step to do that was to assume that croplands are not relocated across national borders, but within national borders. And the results for this are shown here. So this is again a map of the current distribution of croplands. This is a map of the optimal distribution if you relocated croplands within national areas. These were our previous results, and for this national relocation of croplands, optimal national relocation, the reductions of the impacts are still extremely high. So you wouldn't have to move everything across the world. Capital and labor can stay within countries, and you'd still have these massive reductions. Another sort of attempt to make this more realistic is to look at what would happen if we only relocated part of agricultural production and left other areas in place where they are right now. So just ignore the lines for the moment. What's important is essentially the points where the curvature is greatest. That's what we're going to focus on here. What this shows is on the x-axis, you have the possible reduction of the carbon impact. On the y-axis is the reduction in the biodiversity impact. This is the scenario down here at the bottom left that we already looked at. So almost 90% reduction in biodiversity impact, over 70% reduction in carbon impact. And what the lines show though is that what would happen if you relocated only a certain proportion of the production. And the scenario we looked at so far was that if all production was relocated, but what you can see here is, you have to imagine a little dot here, and there, is that even if you relocated about, let's say 10% or so of production, 10% is really not very much, then you'd already reduce biodiversity impacts by over 50% and carbon impacts by almost a quarter. And we have similar results, of course, not that extreme, but on a similar order of magnitude if we relocate croplands within countries. Okay, finally, less and even so far, all the results that I've shown assume that on new croplands, production is totally optimized. So we use agricultural machinery and optimal cultivars and perfect fertilizer and pesticide application. And I mentioned at the beginning that there are yield data also for scenarios where this is for scenarios where the crop management on new areas is assumed to be less intensive. And essentially the takeaway message, without going, because I'm looking at the time, the takeaway message here is, even if the production, so if the production on new areas is less intensive, that will automatically require more land and therefore will also increase impacts. So the potential for decreasing impacts is lower in the scenario where we use less intensive production on those new areas. But the bottom line here, without going into the details, is that even if you relocated areas and then farmed in a very in a not intensive way at all, then there would still be considerable environmental benefits. Okay, just a quick word on how can this be implemented in practice. Well, actually, it has already been implemented. So in the paper, we discussed a couple of case studies, in particular one from China, where I think off the top of my head, I think it was over 100 million hectares of cropland that were effectively relocated in the course of a reforestation scheme that was specifically aimed at reducing soil erosion, actually, but then had significant carbon and biodiversity benefits as well. So the general idea of how can this be implemented is through financial compensation to farmers, in incentivizing them to allow all or part of their cropland to regenerate, to recover those original carbon stocks and biodiversity, and then to incentivize the expansion of agricultural area in other parts of the country or the world where it's more suitable, where yields will be higher and where impacts will be lower. And even in the EU, there was a scheme like that. So we wouldn't have to start from scratch in terms of policy. Okay, final slide is this one. You might be wondering why you're looking at a pan of mushrooms providing in garlic oil. The reason for that is, I mentioned at the beginning, we kept the total production of each crop constant in this particular analysis, but as a different project that I worked on, where I sort of relaxed that assumption and only kept constant the total amount of nutrients that were produced, so allowing even radical diet shifts, so long as the amount of nutrients is produced that we consume at the moment, all sort of shifts between crops were allowed. And one of the results I obtained there was that one of the lowest possible carbon biodiversity impact dishes was one where it consisted, I think, about a third of mushroom and a third of garlic. This is just to say that if you combined, I think, the strategy of relocation with the strategy of diet shifts, that would probably reduce impacts even more. So what I estimated for this particular study, where diet shifts were allowed, was another reduction of about an order of magnitude of impact. So if you combine these two strategies, the impact reduction would likely be massive. Okay, and that concludes the presentation, a few minutes too long. And yeah, looking forward to questions.
Thank you so much, Robert. It's really interesting research. And I've just kind of a very quick question I wanted to ask you. What's taking so long to come to this sort of conclusions or data? Is it because until now there was not enough data, focus of research?
So I think it's, yeah, there are obviously data constraints, but I think it's also a relatively radical strategy that I haven't seen so much in the literature before. So there's a lot on, there are of course different strategies for reducing environmental impacts of food production. One of them are these diet shifts. Another one is to try and increase yields, especially in developing countries where they're often very low. And once you increase those yields, you reduce the area that's needed for production, so that reduces impact as well. But none of these strategies, all of them are moving much more slowly than we would need them to move, and so we introduced this as an additional possibility. And the message that we tried to convey in the paper and also in the press release, which Cambridge was very supportive with, was that even doing this at a very small scale, so even relocating just 1% or 5% of production of the worst possible areas would already have huge environmental benefits.
And are you taking this research further? Are you in discussions with various national governments or lobby groups?
Yeah, I was actually a little bit to my surprise, because you know how it normally is with academic research, it gets published and then nothing happens. But I was contacted by a couple of agricultural companies that expressed interest in implementing this. So they were interested in particular so one of them was an investment company that said, we would like to know where these optimal areas are for future investment in agricultural land. And that's exactly how it should work. If government then incentivizes developing these optimal areas, then it would automatically drive people there. Yeah. So as I said, at the moment I'm personally working on something else, so I don't have too much time to take this further. But for me, this is more of an avant-garde study, and then now is the consolidation work that's needed, doing this at smaller scales.
So maybe I can also follow this up with the rest of your colleagues and see if we can maybe put more pressure on various groups and create connections. That would be wonderful. A very last question, and then I open up. Given that now you're looking at migration, how much then this research and this modeling looks at or takes into account the political situations or conflicts, etc.?
Yeah, so in this paper, not at all. We've completely ignored that, but also made it very clear throughout the paper that, of course, this in its most extreme form, this assumes socioeconomic changes that are just completely unrealistic. But we are very transparent about that. Again, the takeaway message is doing it at a small scale, and these sorts of, as I mentioned also in the talk, at a small scale, things like that have already been implemented. So we have reforestation programs where people give up agricultural land and take on a different profession, move to a city, whatever. In many cases, there are agricultural subsidies that keep people in place and keep them farming in areas where we shouldn't keep farming. Reducing those subsidies would automatically mean that people move to probably urban centers. But what we're saying is this can be implemented. There's a continuous spectrum of implementation, so this can be implemented at a very small scale where the socioeconomic impacts would be small. So.
Yeah. I have more questions, but I want to open up the discussion to the group. Please, questions or comments for Robert or for anyone else in the group, of course. David.
Hi, Robert. Really interesting talk. So I just had a quick question about when you were talking about the reallocation and assuming that it was at sort of maximal efficiency, super intensive. did that factor in the potential carbon emissions and production impacts of fertilizer that would be involved?
So we had a reviewer inquire about that, and the response we gave that was essentially then taken out of the paper by a different reviewer. But our logic was that there is a strong correlation between the production level and the fertilizer use. So our logic was, as long as the total production is the same, the fertilizer use will also be the same. So you use little fertilizer on less intensively managed areas, a lot of fertilizer on very intensively managed areas. But if the total production is the same, then the order of magnitude of the fertilizer use should also be similar. That's what the data that we looked at are suggesting. But you're completely right that that there may be differences there. Yeah, we only looked for the emissions. You could also obviously look at lots of emissions. Another one that we did not look at is transport emissions, which is a question I often get because when you relocate everything, obviously the transport is different. But transport emissions tend to be overestimated sometimes. They do not account for a lot in the total carbon budget of total emission budget of food production.
Okay, great. So, but I guess like loosening that or introducing that degree of freedom could lead to sort of more interesting optimizations as well, potentially.
Yeah.
Cool. Thank you.
Thank you, David. Anyone else? Because I would like to follow up, if I may. Okay. Have you also looked at what would be the impact on relocating land as used for livestock?
Yes, actually, in the very first version of the paper, we included pasture lands as essentially as just another crop that produce where grass is being produced, and that included that and all the impact reductions suddenly doubled in a good way. So it's not 20 years of carbon emissions that were being saved, but suddenly 40 years, because pastures are just so big that relocating them optimally would have the same effect. One of the reviewers wanted that removed from the analysis because they said livestock production is a whole nother story. You can't easily, you'd have to move livestock around before it can get slaughtered, and that gets terribly, terribly complicated. You would have to move a lot of infrastructure around. With crops, it's a little bit easier. And so actually we said, okay, that's fine, but the exact same logic would apply to pasture lands. Yeah.
Right, I understand. Anyone else has questions or comments? Diane, please.
Hi, I was wondering whether soil stability is a measure at all that you use. I was looking at that example of the trees. I assume that's the Loess Plateau in northern China, which erodes very easily. Is that a sort of measure that can be incorporated about the improvements in stability?
Everything can be incorporated as an additional type of impact. Yes, we did not account for that. The only thing we looked at with soils is the soil carbon.
Right. Yeah.
But yeah, you're completely right that could be included. The framework is such that whatever your favorite impact if it is fertilizer emissions or whatever, it can just be integrated in the same way as we did with the other impacts.
Thank you, Diane. I will share, Robert, I'll share the website of that software that you were looking at through FAO.
Yeah.
I
think that those are, I was really, because oftentimes these sorts of data, they're very inaccessible and you need to have a lot of experience with very particular types of software in order to even load them, let alone analyze them and make a study out of them. But this is a great example of how it could be, because the interface is so easy to use and the data are so easy to download. Highly recommended if you're working with spatial crop data.
And you said that also it's possible to play with, let's call them neglected crops, right? So not just the usual fall, but
that particular website, I think it depends a little bit on the scenario that you're interested in, but there are easily a couple of dozen of crops, oftentimes not major crops exactly. And I think for some scenarios, the number might go up to 40 or so, which is really terrific, because as you say, oftentimes, especially in those global studies, it's usually 4 or 5.
Yes, exactly.
Being looked at.
Anyone else? And questions, comments, please. No more questions or comments. I just wanted to ask you a very final question, Robert. How much have you been working also with Andrew Bamford and the land sparing, land sharing, and all this? Is it part of it?
We had a few interactions. Yeah, I generally, when it comes to this paper, I mean, effectively the results point quite strongly in a land sparing direction, but what we're saying is, even if you manage less land, not so effectively, not so intensively, then the potential for reducing impacts just by the relocation alone is still really big. So we deliberately didn't take a particularly strong position on that, because we know how controversial it is. But between us, yeah, the paper says that land sparing is probably the way to go. But it's debate.
Great. Yes. Anyone else before we wrap up? Any other comments or questions? Robert, would you like to? Yes, David, please.
Sorry, one final follow-up. I was wondering if you had any thoughts on sort of what are the biggest weaknesses, or sort of say in the input data, what worries you most about sort of the inputs going in that could lead to sort of misleading optimizations, and where people should focus for future work?
Yeah, I think so. I think the sort of general the key spatial patterns that we identify, those hotspot areas where it's most likely most optimal, most best to grow crops in terms of getting as much yield for as little impact as possible. I think those are probably quite robust. But I think all of the data sets that went into it, as it is the nature of global data, there are uncertainties. Often these uncertainties, unfortunately, for none of the data sets that went into this analysis, we only use pre-existing data. Uncertainties are never available, although they kind of should be, especially for those modeled potential yields in areas where certain crops are not cultivated at the moment. There's usually an uncertainty that would come out of a model, but oftentimes that's not being made available, which is a bit of a pity. But I think if I had another 10 years to consolidate everything we've done here, you probably use independent data sets for the carbon stocks, and for biodiversity there's really not so much that you can use, but for the yields there are lots of different crop models that differ slightly in their output, so you can quantify those uncertainties if you wanted, but all of the different data come in different formats, which is such a pain. So we focus on this, and but it's a valid point. Yeah.
Did you find, Robert, when you were doing the research, that there was transparency in sharing data?
Yes. I think we only had one negative experience with someone who demanded the co-authorship in return for data that had already been published. I don't appreciate so much, but none of this. So this person did not end up on the paper. We used an alternative data set in the end. But in general, yeah, especially I can't say often enough, especially the potential crop data. I mean, this is transparent. This is one of the best examples of transparency, because not only are the data available, but they are available in such an easy to visualize and analyze format. So yeah, the overall positive experience.
That's great. Oh, it's a very positive research, really, and gives some good energy. I see that Stephanie has a comment. She says that they have some of the calibrations for the crop models from the past 20 years of production. Stephanie, I don't know if you're able to open your mic and may ask the question or make the comment. Yes, you can. Oh, great.
Yeah, I'm here. I'm just finding my other camera. I'm in the grass here. Literally, yeah. So
Stephanie,
Robert,
would you like to say where you? I know you, of course, but
sure. Robert, it's a pleasure to meet you. I'm Stephanie Race. I own two different companies, and we're based in the U.S. and in the UK. And we started 13 years ago doing crop yield forecasting and biogeochemical modeling at the field and farm scale. And we also work not just in crops, but in pasture land and then in other land use classes at the catchment scale. So we built an informatics platform. So we have run hindcasts on most of the geographies that you represent in your study, and we're up to 63 different crops, so broadacre, perennial crops, tropical agriculture. And we've run calibration data and done a lot of ground truthing. So we have an extensive data sets on, how do I say this, the uncertainty associated with forward-looking data in the context of how these models have actually been calibrated based upon past measurements. And I think the research you've done is great. I've sent it to a couple of scientists on our team from the International Institute of Applied Systems Analysis and Colorado State University, and Rothamsted are some of our partners. So you'll know the people, but we took a best of breed approach from we have 6 different biogeochemical models and something like 52 different crop models. So we've done an enormous amount of work in testing out all these different models and ground truthing the observations, you know, through work with growers. I think the one question I'd have for you, and you can answer this now or offline, has to do with the simulations on forward-looking precipitation data and temperature in terms of how would I say this, what the spatial distribution of that information in terms of its accuracy relative to what we can expect in terms of, you know, increased photosynthetic activity versus, you know, what are you actually looking at from a yield point of view? Because we've done some work on this in terms of these multiple simulations under different conditions of climate change, similar to work that David LaBelle has done, but we've done it with, how do I say this, yield models with actual management data, as opposed to just looking at remote sensing and some crop coefficients. I guess that's just a question. I know it's fine tuning because you have the accuracy of these forward-looking attributes in terms of how accurate they are, and then how it actually plays out is always in the context of how disrupted the water cycle is in a given geography. That's been our experience. I'm going to take myself back on mute again, but so I have more detailed questions than probably you have time for today, but those were some of my questions.
Great. Yeah, thanks so much. Yeah, that sounds like fantastic work that you're doing. I can't say too much I can't speak too much to how the crop yields were estimated based on. So what I do know, but all of that is on the FAO website that I mentioned, is that they applied their crop models to a series, maybe half a dozen or so of climate model simulations that I think operate on at a diurnal timescale, and then so these should simulate dry spells, cold spells.
I think that our experience with the FAO data, the things that it's not accommodating for are you know, pest and disease, and how different varieties actually play out in different soil fertility scenarios and disruptions to the water cycle in terms of like surprise drought again, or we've got a hurricane in Mozambique, and so all bets are off and we have to rerun these simulations. So there's another, I would say, level of simulation on the forward-looking data that has to take those El Nino, La Nina cycles into account on some of this data, because our experience so far has just been, you know, looking at extreme weather events, business as usual, as opposed to what we're actually seeing in terms of drought and fire and hurricanes and flooding are the primary factors that disrupt what these forward-looking forecasts actually generate. Okay, I'm going to stop talking now, but I really love the paper. I sent it to my team. I asked for their feedback, and we'll be in touch on email.
Great. Yeah, these sorts of events are difficult to predict for sure. And you mentioned pest. I think for that, I mean, those FAO data, I think, are also just very much constrained by the data that's available at a global scale, because I think with pests, I would not know where to even start. Even for something as fundamental as soil, global data sets are just so poor when it comes to biochemical properties of soil in a given location. Sometimes the data is so terrible that you have to interpolate in ways that are very problematic.
Yeah, it's a shame that John has left because he had another meeting because he's a virologist. He would have certainly be able to help with. But maybe Robert, I'll try to put also in touch Stephanie and John, maybe also with Andrea, who possibly is continuing this research.
Don't think so, not for the moment.
Okay.
But,
okay, hopefully we'll see how we can push this forward. But thank you so much. Unless anyone else has any more comments or questions, I would like to thank Robert to join us today. There's been really interesting and fascinating discussion. I thought also, closing the week with a positive note, hopefully. And I hope to see as many of you as possible next Friday to talk about plants under stress, climate change again, with Angie Garner from Plant Sciences. So I hope to see you 2 o'clock next Friday. And in the meantime, have a good weekend. And you can find the recording, of course, on our page. So if you want to share, please do. There'll be slides if I manage to get them from Robert and the recording. Wonderful. Thank you very much, everyone. And
thanks, everyone. And thanks again for the invitation, Francesca.
Thank you, Robert. Have a good weekend. Cheers.
Bye. Thank you.
Bye. Bye. Bye.